Oh boy, that's a hard way to start the whole Pluto business. I'd like to apologize on behalf of everyone involved in that. So hi everyone, thanks for that great introduction, and again my name is Travis Rector, so I'm a professor of physics astronomy down at UAA, the sister campus just down the road. And so in addition to my astronomical research, one of the things I do on the side is I make astronomical images using many of the telescopes here on the ground, like those at Kitt Peak and Gemini, but also telescopes like Hubble and Chandra up in space. And you may not know me by name, but hopefully you've seen some of my images over the years. So for example, this one, and this is probably my most famous image right here. It's of the Helix Nebula. It's also known as the Eye of God, and this image has gained some fame lately because Neil deGrasse Tyson used it for the opening of his reboot of the TV show Cosmos. So I'll point out they modified this image to look like an eyeball, which I thought was kind of silly because it already looks like an eyeball. But you may have seen this image as well. So after I graduated from the University of Colorado, after getting my doctorate there, I then became a postdoc at this place right here. This is Kitt Peak National Observatory, which is in southern Arizona, about 40 miles west of Tucson. And I got there in 1998. And at that time, they were just commissioning a new wide-field imaging camera called Mosaic. And this is a picture of Mosaic right here. It's the big black and gold box sitting at the bottom of the telescope. And Mosaic is a camera we're still using today, and it has it's a 64 megapixel camera, so it's 8,000 by 8,000 pixels on the side, which even by today's standards is a pretty good sized camera. But in 1998, it was insanely large. How many of you had a digital camera back in 1998? How many of you remember 1998? Okay. So when this camera was first built, the hard drives at the time, the largest hard drive I had was a 10 gigabyte hard drive. And each image that came off of this camera was 300 megabytes. So if you do the math, that means we could only have about 30 images on our computer at one time. It was very challenging processing the data coming from this camera. And this camera was a new breakthrough in astronomy because it had a relatively large field of view. It had a field of view that is 1 square degree on the side. And so to give you a sense of what 1 square degree is, if you hold your thumbnail out at arm's length, and you can go ahead and do that, your thumbnail is about 1 square degree in size. Does that look like a really wide field of view to you? Does that seem like really big? What do you think? Not very big. Well, for astronomers, it's huge because we are used to zooming into very small portions of the sky. So this camera, we wanted to show off to our fellow astronomers what it can do. And so so when I was a postdoc there, they asked me to make some images, and the first image I ever made was of the moon. And what I did is I took a picture of the moon, and then I waited 2 days for the moon to move out of the way to another part of the sky. And then I took another picture of that same location of the sky, and then combined the two. And this image right here is to show the field of view of this camera. So again, this image here, the moon and the stars behind it, is the size of your thumbnail, as held out at arm's length. So when we look at the moon, we think of the moon as being this just gigantic object up in the sky. And that's an optical illusion caused by the fact that we usually see the moon close to the horizon, so we see it near buildings and mountains that in our mind are very big, so we think the moon is big as well. But next time you see the moon out, which if you live here in Fairbanks will be in a couple months, hold your thumb out at arm's length, and you'll notice the moon is only about half the diameter, half the size of your thumbnail. Now, the second image I made with this camera is actually this guy right here. This is of the Rosette Nebula. And one of the things I'd like for you to take away from my talk tonight is that many of the objects we look at in the sky, many of the pictures you see, are actually of objects that are very big in the sky. So the Rosette here is actually much, much bigger than the moon, not only physically in size, but also if you were able to see it up in the sky. If you were able to see the Rosette Nebula with your eyes, it would actually look quite a bit bigger than the moon. So people often think that the things they see pictures of are things that are invisible to them because they're too small. And that's sometimes the case, but it's also true that many of the objects you see are actually quite big, but just simply too faint. And so that's why we use telescopes. So I did this when I was a postdoc at Kitt Peak, and I learned an important lesson that all of you kids in the audience should remember, and that is, you do something once, it's a favor. You do it twice, it's your job. And so the staff there were happy with the images I made, and they said, would you be willing to make more? And I said, sure, it's fun. And so I started making more images for Kitt Peak, and I also started making images for other observatories, including this one right here. It's called Cerro Tololo Inter-American Observatory. It's in northern Chile in the Atacama Desert. And you'll notice that, like Kitt Peak, there's a lot of dirt there. And that's because we like to put our telescopes in high and dry locations, up in the desert, on top of mountains, where there's very little water. I also started making images using the Gemini telescopes. As you might guess from the name Gemini, it's a twin set of telescopes. Each one is 8 meters in diameter, and there's one on the summit of Mauna Kea on the Big Island of Hawaii. So yes, I do get to go to Hawaii for my work. And the other one is down in Chile as well. So for the last 20 years or so, I've been making these astronomical images, and people often ask, why do we make these astronomical images? And the first and most obvious reason is to help visualize scientific results. So for example, this is a picture of a nearby spiral galaxy called M101. And if you look in the upper right corner, you'll see a bright star there, and that's actually a supernova that exploded inside this galaxy. So we took a picture to show this star that was exploding inside this galaxy. So that's the first reason we make images. We also make astronomical images to demonstrate new technologies that we have. So for example, this picture right here shows what are called the bullets of Orion. These are stars that are being shot out of the constellation of Orion at super high speeds. And as they do that, they leave these wakes behind them, just like a high-speed boat going across a river or a lake. This picture right here is actually of a higher resolution than what's possible with the Hubble Space Telescope. And that's because we use a new technology called adaptive optics, which corrects for the blurriness of the Earth's atmosphere. So on the ground, we can actually sometimes do better than Hubble. And then finally, we also make images of space to share with people some of the spectacular views of things that we can see out in the universe. So basically to share with the public the kinds of cool things that we're studying with the telescopes. Now, over the years, there's been lots of questions about whether or not our images are real. And I recently stumbled across this Calvin and Hobbes cartoon. For you young ones in the audience, Calvin and Hobbes is the greatest cartoon ever created, and you should go find it. Thank you. It was a gratuitous thing, I said. And I love this cartoon right here because it was made before the days of Photoshop. And so even back then, there was questions about whether or not photos are actually real. So over the years, I've been showing my astronomical photos to people, and they often ask questions like this. Is this what it really looks like? Or are the colors real? Or my favorite is, if I were standing right next to this, is this what I would see? Now, I don't really know what it means to stand right next to a galaxy, because that's something that's usually several 100,000 light years across. But basically, all these questions are getting to the idea of, is this what I would see, or if I were closer to it, or is this thing actually really real? And so to illustrate that concept, what I do is I show people this image right here. And what this is a picture of a famous astronomical object called the Horsehead Nebula. And this is taken with the same mosaic camera that I told you about before. So this object right here is actually bigger than the moon. And this picture right here is what it looks like to our telescope. Now let's imagine you got into a spaceship and you were to fly the 1,000 light years or so out to this nebula, and then you get there and you look through the window on the spaceship. This right here is what you would see. So a remarkable thing is that even though you're much closer to the nebula now, you still can't see it. And this has to do with something called surface brightness. Surface brightness is simply the ratio of how much light you get from an object to how big it appears. Now, as you get closer to the nebula, you're getting more light from the nebula. That's called the inverse square law, if you remember that from your physics class. But as you get closer to it, it's also getting bigger. And so that ratio cancels out. And this is something you can actually do at home. If you walk towards a wall, the wall gets bigger, but it doesn't get any brighter. And what that means is that if you can't see the nebula from here on Earth, you still won't be able to see it even if you're much closer to it. And as I said before, this image right here is of a field of view that's the size of your thumbnail. It's twice the size of the moon, so it's plenty big. If the nebula were bright enough, you could easily see it with your eyes, but you can't see it because it's too faint. So when people ask me questions like these, is this what it really looks like, or the color reals and so on, the answer is almost always no. Now, in the case of when you're looking at things like the surface of Mars, you've probably seen pictures of the Martian rovers as they're driving around on the surface. Those pictures you're seeing are very close to what your eyes would see. And that's because Mars is a place that's lit by the sun. And even though Mars is a little bit further away from the sun, it still gets enough sunlight that you could easily see what's going on the surface. But most of the objects you see, the astronomical objects you see, are objects that are too faint. So even if you were to get much closer, because of the surface brightness, you still wouldn't be able to see them. Another problem is that our eyes are really bad at seeing color. If you look up at stars in the night sky, some of the stars are bright enough for you to see color. So, for example, Betelgeuse is a bright red star in the constellation of Orion. That star is bright enough that you can actually see that it's an orangish red. But pretty much all other stars, that when you look at them, they just look white because they're not bright enough for you to actually see the color. And in particular, our eyes are really bad at seeing red light. And so when you ask what color something is, you have to take that into account. So for example, if you look at even if you were to look at the Horsehead Nebula through a really big telescope, it would actually look blue to you because your eyes are much more sensitive to the blue-green light coming from the gases inside that nebula, but not as sensitive to the red light. And then finally, there's kinds of light that your eyes can't see. All the colors of the rainbow that we can see we call optical light or visible light, but there's all these other kinds of light as well, so things like X-rays and radio waves and infrared light. And these are kinds of light that are either too high of energy light for our eyes to see, or they're too low of energy of light for our eyes to see. And so Kim Arkand, who's one of the co-authors on my book, has a really great analogy, and that is, imagine you have a piano keyboard in front of you, and there's all 88 keys there. And imagine your ears were such that you could only hear middle C. So it would just be ding, 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 ding. And now let's imagine someone's playing a beautiful Debussy piece, and all you can hear is that one key. Not very exciting, is it? Well, unfortunately, that's your eyes. All this incredible light is in the universe in the form of these other kinds of light, and your eyes can't see them because your eyes are pretty darn good for getting around here on the surface of the Earth, but out in space, you'd be dead. So when people think of telescopes, they usually think a telescope does just one thing, and that is they think that a telescope is like a giant pair of binoculars, and that is it magnifies something to make something that's small and far away look bigger and up close. And while it's true that telescopes do that, there's other things they do that are just as important. In particular, they collect lots of light. They allow us to collect light from faint objects so we can not only magnify an object, but also amplify it. That is, make something that's faint look brighter. And then finally, it expands our vision. We have telescopes and cameras that can see all the different kinds of light that exist in the universe, not just that little portion of light that our eyes can see, that middle C. So one way to think about it is that as you look out at the world and your eyes are telling you about what you're seeing, all the light that you see when you look out is coming into this just little teeny tiny hole in your eye that's called the pupil. Now the size of that pupil will adjust depending on how much light there is. You've all had that effect that if you are in a movie theater and then the movie ends and you walk outside, you have that blinding effect. Well, even when your eyes are dark adapted to see faint light, that eye opening, that pupil, only gets to about a quarter diameter in size. So it's a very small opening for light to come through. Now, for comparison, the mirror on the Gemini 8-meter telescope, 27 feet for those of you who are metrically challenged, is a much, much bigger mirror. So this is a picture of the mirror, and it's 8 meters or 27 feet across. And to give you a sense of scale, that's a person in a white clean suit standing at the center. Now, what you're seeing here, this surface of the mirror that surrounds the person, that's what actually collects and reflects the light from whatever we're looking at. So at any given moment, this mirror is collecting over 1 million times more light than what your eyes are seeing. And not only that, we can use our telescopes to take long exposures. So your eye works like a movie camera. It's taking pictures 30 times a second. So each exposure that your eye takes is only for 1/30th of a second. But our telescopes are built to track the night sky, and we are able to collect light from objects for many hours. And so this is a picture of the Gemini telescope in action. And you can see the stars moving in the background. As the Earth turns, the sky rotates, and the telescope moves with it. So we're able to follow an object. So what we can do is with this telescope is we can not only collect lots of light at any moment, we can do it for a long period of time. And that allows us to see objects that are much, much fainter than what our eyes can see. So next thing I want to show you is a picture showing something called the XDF, or the Hubble Extreme Deep Field. So this is a picture of space that was taken by using the Hubble Space Telescope and staring into one location in space for 50 days straight and collecting all of the light that came from it. The first time they did this, it was called the Hubble Deep Field, and then they did it again, and they called it the Hubble Ultra Deep Field. And then this time they did it, they called it the Hubble Extreme Deep Field, and I don't know what they're going to call it next time, but it's probably going to be like the Hubble Ludicrous Deep Field, or the Hubble Absurdly Absurd Deep Field, or oh my God, you won't believe how deep this field is field. And so what they did is they looked at, see that little tiny square in the middle there, a little diamond, it says XDF next to it? That's the field of the Hubble Space Telescope. And I show this picture because the big square here that says 1 degree across on the side, that's the size of your thumbnail, or that's the size of my wide field camera on Kitt Peak. Now some people have asked me, well, why did Hubble look right next to the moon? That's a dumb idea, because isn't the moon really bright? Well, they weren't actually looking next to the moon. The moon's just put there to scale. But what they did is they looked in this little black square here, which in that picture up there, it looks like there's nothing in that square. And they stared at it for 50 days straight, and then in the end, this is what they saw. Is that little black square that looked like it was empty is actually filled with thousands of galaxies. Each of those little fuzzy smudges in there, with a few exceptions, is a galaxy that is billions of light years away from us. And so this is the deepest image ever produced, and those little fuzzy smudges in there are about 10 billion times fainter than what your eyes can see. So it's a nice illustration of how the power of telescopes allow us to see things that are literally invisible. And it makes sense. What would be the point of building something like the Hubble Space Telescope if it just showed you what our eyes can see? Now, to produce these images, we use a technique where we take many images of an object through multiple filters. And that's because our digital cameras, very much like the ones in your phone, do not necessarily see color. And so this is a black and white picture of a nebula called the Crescent Nebula. And this is taking a black and white picture through just one filter. And then what we can do is we can take pictures through multiple filters. This is a picture of the filter wheel on our camera. So each one of those color squares is a filter that the camera looks through. And so we can take like a picture through blue and then red and then green, and then we can combine them all together, and then we can produce a final color image that looks something like this. So when we create images in astronomy, we often create images in a way that mimics the way your eye sees color. The way your eye sees color is that inside your eye there's detectors that are called cones, and there's actually 3 different kinds. There's what are called the S, M, and L cones. The S cone stands for short wavelength, which sees blue light. The M cone sees mostly green and yellow light, and the L cone sees yellow to red light. So if you're looking at someone's shirt, like this gentleman's shirt here right here is blue, the reason why I know it's blue is because the S cones inside my eye are getting more light and getting more excited than the M and the L cones, and then my brain is able to figure out he's wearing a blue shirt. So we do essentially the same thing. We can use filters that essentially cover the same colors of light as the S, M, and L cones. So on the left here is a picture of some of the filters that we use. And you'll notice there's what's called the B, V, and R filters. And those B, V, and R filters are very closely matched to the S, M, and L cones. So sometimes astronomers produce what are called true color or natural color images. And these are usually images made through these blue, green, and red filters in a way that mimics the way our eyes work. But there's actually other kinds of filters that we use as well. So filters that can see ultraviolet light or infrared light. And we also have special filters that are designed to see what are called narrowband types of light. And narrowband types of light are when we're looking at very specific colors of light. And I'll talk more about those in a second. So what we can do is we can make an image by looking at an object through many different filters, and then we can use the colors we see in each of those filters to combine them together to produce the final color image. So this picture right here on the left shows a picture of a nearby galaxy called NGC 6822. And that picture is using just 3 filters, just the blue, green, and red. And then the picture on the right is an image of the same galaxy where we actually used 8 filters. And so by using many different filters, we're actually able to collect more and different kinds of light, and so we can make a richer image. In particular, if you look at the picture on the right, you'll notice there are these little red clouds of gas inside the galaxy that are more visible when we do that. So to create these images, what we do is we can look at an object through these different kinds of filters and then combine them together. So this is a picture of another galaxy called M33, and this is what the galaxy looks like through the blue filter. And when we look at this galaxy through the blue filter, we're mostly seeing the light from the hot blue stars inside the galaxy. Now this is what the same galaxy looks like if we look at it through a special filter called a hydrogen alpha filter, which is designed to see a specific color of red light that our eyes can just barely see. And you'll notice that it looks very different. So if I go back to the previous image, this is what it looks like in the blue, and this is what it looks like in hydrogen alpha. So the blue filter shows us where the hot blue stars are, and the hydrogen alpha filter shows us where the hot hydrogen gas is in the filter, in the galaxy. So to create the color image, what we do is we give a color or assign a color to each of the different layers. So the hydrogen alpha we made red, because that's what color it is. And then we looked at the same galaxy through what's called an infrared filter, and we made that orange. And a good question to ask is, well, what color should I make light that your eyes can't see? And infrared, as you might guess from the name, is a kind of light that's just below red. And I made it orange because I'm already using red for the hydrogen alpha. And then each of the other filters, I gave a color and order of their energy. So this is, so we're going through the different colors, the green, the blue, and then we get to what's called the ultraviolet, which is again light your eyes cannot see, but I made it violet. And then when you combine them all together, this is the final color image that you get. So this picture of this galaxy was created by using 6 different filters. And the reason why we did that, if we zoom in on the galaxy here, you can see that by using all these different filters, we can see all the colors inside the stars, and we can also see the glowing red hydrogen gas in this galaxy where new stars are forming. And one of the amazing things about astronomy is we can actually use the colors of stars to determine the temperature of the star. We don't have to fly all the way out there in a spaceship and stick a thermometer in the side of the star, which doesn't work for a whole lot of reasons. We can just look at the different colors, and the blue stars are the hot stars, and the yellow and orange stars are the cool stars. So we can actually pretty accurately measure the temperature of a star just by looking at its color. So hydrogen alpha, as I mentioned before, is a specific color of red light produced by hot hydrogen gas. But there's actually other types of colors of light that are produced by other types of atoms. And so, for example, there's a specific color of red light produced by hot sulfur atoms. Now, this color of red light is very close to the red light produced by hydrogen. And your eyes can't tell them apart, but fortunately our cameras can. And so we can use these special filters to differentiate between the light from the hydrogen gas and the light from the sulfur gas. And so we can produce images in a way that's very different than the way your eyes see color. So this is a picture of the Eagle Nebula. And this is what it looks like through the sulfur 2 filter, which I made red. And then the hydrogen alpha filter I made green. Now, hydrogen alpha, if you saw it with your eyes, would look red. But since it's very close to sulfur 2, I decided to make it green so it stands out. And then finally, we used a third filter called an oxygen 3 filter, which lets the light from hot oxygen to pass through. And then when we finally combine all three, this is the color image that we get. So this image right here is not the way your eyes would see it, but is instead a way of showing the different types of gas inside the nebula, and in a way where the colors actually correspond to temperature. So the blue areas are the hotter areas, and the yellow and green areas are cooler. Now we can use the same technique for infrared light and X-rays. So for example, in infrared light, we can make a picture where we see low energy infrared light, we make it red. Then middle energy infrared light will make green. Higher still will make cyan. And the highest energy infrared light we make blue. And then this is the final color image that comes out. So this is an example of what's called chromatic ordering, which is that we, even though we're looking at infrared light, we use color in a way very similar to what your eyes would see. So the challenge when we make these images is we have all these different kinds of light, and we have all these different kinds of filters. And so the challenge is, how do we make an image that effectively shows what's going on in there? So the next thing I want to talk about is how we actually use some techniques in the art world to help us make science images that are intuitive. Now, when you're looking at something like me right now, or if you're looking out at something in the distance, you may not realize it, but your brain is going through a whole bunch of complex calculations to create a three-dimensional map of what it is that you're seeing. Because, of course, when you're looking at something, you're probably thinking about, well, am I going to go walk there, or am I going to interact with something, or is that little brown dot off in the distance a bear, or, you know, should I be running right now for my car? What should I be doing? So to illustrate this, I wanted to show this picture right here. So when we're looking at something, our brains are interpreting it, and we use something that artists call visual grammar, which is how our eyes and our brains read an image to understand what it is. Now, looking at this picture here, I have a question for you. Which half of this image is closer to you, the top half or the bottom half? What would you say? The bottom half. That's the easy part. The second part is, how do you know that? What's that?
It's clearer, the colors are brighter.
Okay, so it looks clear. The things in the top half look fuzzy. That's an important part of it. I heard something else over here. Is there something?
Well, I just said less haze.
Okay, so less haze. So that's essentially the same thing she's saying right here. So the top half, it looks hazier. So what causes haze? Does anyone know what that is? Why is the top half hazier? Okay. Yeah, that's right. If you're in Fairbanks, it's smoke, right? Because here in Fairbanks, you have 2 seasons, -40 and smoke. So, okay, so there's water vapor, there may be dust, or there's just material in the air. But simply said, there's air. And so the sky is blue, and that's because as sunlight comes into the Earth's atmosphere, it is scattered off of dust in the atmosphere. And that blue light causes the atmosphere to be blue. So when you look at this image, the top half looks bluer, and our brains naturally interpret that as meaning the bluer it is, the further away it is. Now there's some other visual cues here as well. So for example, we are all familiar with those green-looking things on the bottom. And it's a natural intuition for our brains to say that if we see things that are of similar shape or appearance, that the smaller ones must be further away. And so that we interpret the trees off in the distance as being smaller than the ones near, because we can see the leaves on the nearer ones look bigger than the ones in the distance. Now, when the Apollo astronauts went to the moon, they landed in a place that didn't have an atmosphere. And it turned out it was actually really hard for them to figure out where they were. Because here's a picture of the Apollo 15 lander. And if you look to that thing to the left of it, it's not clear whether or not that's a large mountain off in the distance or if that's a hill just right behind the lander. And if you take a second with your brains, you can actually convince yourself of either one. So the Apollo astronauts actually at first struggled mightily to figure out where the heck they were going on the moon because they lacked that visual cue that we have. There was no atmosphere, so they weren't able to tell the distance. Now, the reason why I mention this is that when you look at an astronomical image, you're often looking at something that's exotic and very different than what you're accustomed to seeing here on Earth, but your brain is still processing the image. So this right here is a picture of a part of what's called the Lagoon Nebula. And when you look at this image, your brain will naturally interpret the blue and green areas, which artists call cool colors, as being behind the yellow and red areas, which artists call warm colors. So this is actually a technique that artists have been using for years to manipulate you into seeing depth into images as you look at them. Now, to convince you this is a real effect, here's a picture of an object called the Keyhole Nebula, and this is showing it in color on the left and black and white on the right. And I think you'll agree with me that the image on the left looks a lot more dynamic. It looks like there's depth to it. It looks three-dimensional, whereas the image on the right looks really flat and abstract. Now, we use colors in other ways as well. So, for example, we're accustomed to thinking of red things as being hot and blue things as being cold. And that's because most flames we see are red, and ice looks bluish in color. And as you may recall earlier, I said that's actually just the opposite of stars. The blue stars are the hot ones, and the red ones are the cold ones. We're not accustomed to having blue hot things here on Earth because usually when something gets hot enough to emit lots of blue light, it either melts or explodes. So we usually have like red hot and then maybe white hot, and then you get melt hot. So you don't actually have blue hot here on Earth. But stars are blue, and those are the hottest things out there. So we normally think of blue as being cold. So we use this when we create our images. So this is an example of an image I made many years ago. And this is an image where we took a picture of the same triangular galaxy I showed you before with an optical telescope, the image shown on the left. And the picture on the right shows that image combined with data from a radio telescope called the Very Large Array. Any of you see the movie Contact with Jodie Foster, where she had the headphones on and there's all those dishes off in the distance? We don't actually use headphones when we use radio telescopes. But the cool thing is radio telescopes are designed to detect radio waves. This is a very low energy form of light that your eyes cannot see. Now, hydrogen gas, when it is heated up, will produce red light that our eyes can see, that hydrogen alpha I told you about. But when the gas is cold, you can't see it. It's invisible to your eyes. But our radio telescopes can see it. So the picture on the right shows in purple the radio waves coming from that cold hydrogen gas inside the galaxy. So when we made this image, we had to ask ourselves, well, what color should we make the radio waves? Because radio waves are invisible. Well, if you look closely at this image here, if you look at the very center of the image here, you'll notice there's a red cloud of gas. And that red cloud of gas is a place where there are stars forming, and it's heating up the hydrogen and causing it to be hot enough to produce red light. Now, outside of that hot gas is cold hydrogen gas, and these filaments you'll see are connected to it. So we use purple because it's a mix of red and blue. And so the red would make it blend naturally with the red light inside the cloud of gas at the center, and the blue light tells you that it's colder. So when you look at this image, hopefully you'll naturally intuit that the purple stuff is the same material as the red stuff, but is just colder. I'll admit I probably completely overthought that, but those are the goals that we do. Now, for comparison, I don't have it with me, but we tried using green, and if you use green, it just looks like someone threw up on the picture. So the green doesn't blend at all because there's no green inside that red area. So one of the things I hope you'll take away from my talk today is that when we make these astronomical images, we use principles of artistic design to help tell a scientific story. So sometimes people think it's science versus art. People ask me, well, you're a scientist, so do you consider yourself an artist? It's like, well, maybe. But I'm using principles of artistic technique to tell a scientific story. So when we make these images, we start with what is the science that we want to get across, and how can we create an image that best naturally conveys that science using the wiring in your brain the way you interpret an image. Now, sometimes this actually goes backwards in the sense that sometimes instead of starting with the science and then creating an image, sometimes we create an image and that leads to science. So this is an example of this. This is a picture of what's called the Iris Nebula. And after I made this image, I started looking at it closely, and I noticed that there's these little fuzzy red smudges in it. And I thought, oh, that's interesting. Sometimes I find interesting things in my images and I go look closely at them. And if I looked at just the hydrogen alpha, I noticed that there was a very faint line, horizontal line, that was connecting those little black smudges. And what this turns out to be is it's a jet of gas that's being shot out of a group of stars at where that black plus sign is at the middle. And I know that because we used the Spitzer infrared telescope to look inside that cloud of gas, and we found that group of stars right at the middle, and we could see that jet of gas shooting out. So the cool thing about it is that this image here is that through this image we were actually able to do some cool science, and we were actually able to get a publication out as a result. So over the years, for the last 20 years, I've made over 300 astronomical images, and most of these images are on my personal website. If you Google my name, Travis Rector, fortunately my name is unique enough that only 2 people are going to come up, myself and a guy who's on death row in Texas. So I'm the astronomer, he's the guy, he's the murderer. That's what they think. So. And on my website, I have most of the pictures that I've taken over the years, which include my deep sky astronomical images. I've also taken many pictures with normal cameras at some of the cool observatories and other places that I've gotten to go, including Chena Hot Springs. And I've also made many panoramic images of many of the different observatories and cool places that I've gotten to go. And finally, the reason why I'm here tonight is because through the University of Alaska Press, I've published a new book called Coloring the Universe. And my co-authors, Kim Arkan and Megan Watsky, who work at the Chandra X-ray Observatory, have joined me to create this picture book that shows many of the astronomical images that we've made over the years and also describe to you how these images are made. So talk about a lot of the things that I've talked about tonight as far as how the images are made, what do the colors mean, and things like that. Now, one of the cool things that I got to do as part of the process is to make what's called a book trailer. And I didn't know what a book trailer was till I wrote a book, but a book trailer is like a movie trailer, but it's for your book. So last November, I went down to Kitt Peak and we made this short book trailer, which I'd like to share with you right now. Have you ever looked at an image of space, say like a galaxy or nebula, and wondered, is this real? Is this what it really looks like? Or maybe you even asked yourself, if I were standing right next to this object, is this what I would see? Hi, I'm Travis Rector, and I'm a professional astronomer. For the last 20 years, I've been coming here to Kitt Peak National Observatory in Arizona to make beautiful images of space using the giant telescopes here. Along with my collaborators, Kim Arkan and Megan Watsky of the Chandra X-ray Observatory, we have written a book called Coloring the Universe, which gives you a behind-the-scenes look at how these beautiful images of space are made with the professional telescopes. We're now inside the dome of the Mayall 4-meter telescope. This is the largest telescope on Kitt Peak and is one of my favorite to use. In our book, we have over 300 color images of space, many of which were taken with this telescope. With this, we can see objects that are over 100 million times fainter than what the human eye can see. We're now inside the control room of the 4-meter telescope. This is where the astronomers sit when they're observing at night. When we're observing, we observe from dusk to dawn because telescope time is precious. For every 5 astronomers who ask for time, only 1 will get it. So this computer here is what's used to control the camera that takes the pictures. Behind me is where the telescope operator sits. The telescope operator is the celestial taxi driver. He or she is the one who points the telescope at the object that we're looking at. Professional telescopes like these give us superhuman vision. They literally allow us to make the invisible visible. In Coloring the Universe, we explain how we use these giant telescopes to make color images of space. We hope you enjoy this behind-the-scenes look at how professional astronomers see the universe. Okay, well, thank you. So, I've left time at the end for any questions that you might have, and so I'll take questions for the next 10 or 15 minutes, and then afterwards we will have the book for sale if you're interested. The book normally sells for $50, but we're selling it at the UAF discount price of $40, so if you're interested in getting a copy of the book, we will have them for sale, and I'd be happy to sign one too. So if anyone has any questions, I'd be happy to answer them. Yes, sir?
When you run time, say, at the 4-meter kit telescope, is some of the time that the images are being gathered, are you sitting in your office in Fairbanks downloading data, or are you always down there?
So some of the telescopes can be operated remotely. So the Gemini 8-meter telescopes are operated remotely. For Kitt Peak, you still do what's called classical observing, which is you are assigned particular nights on the telescope, and then you go down to the telescope and use it on those nights. Now, the disadvantage of classic observing is that if you go down on your nights and it's cloudy, you're just out of luck. Whereas if the telescope is operated remotely, if the weather's bad, then you'll just get bumped to a later night. Yes, sir?
You told us that one image was acquired over 15 days. So do you always take, for example, 10 images a second, and then afterwards you calculate them together, and for example take the mean, then you get your resulting image, or how do you do it?
Yeah, so his question was basically, do we take many images and combine them together? And the answer is yes. So usually we don't take a picture that's longer than, say, 15 or 20 minutes. And the reason why that is because, as you saw in the time-lapse movie there, the telescope is moving with the night sky. And the way that it works is that we have what are called guide stars. The telescope will choose a guide star and it'll follow it as the telescope moves, so that way the stars don't streak across the image. But every so often something goes wrong with the picture and the stars will streak and we have to throw that picture away. So rather than wasting like many hours in an exposure, we'll take many shorter exposures and then electronically, so our computers, we can add them up together and it'll have the same effect as taking one single longer exposure. So that picture I showed you of the Hubble Extreme Deep Field, that was one that was made with thousands of images combined together to produce that final color image.
So you gain the resolution out of the amount of images.
Well, what you get is the more images you stack together, just simply the more light you get, so it allows you to see fainter and fainter objects.
Okay.
Yeah. No questions? Yes, ma'am.
The filters, are they all at the same image, or are they different images that are then stacked?
Okay, so your question is, are the filters of different images? And the answer is yes. So we will maybe take like 10 images through the blue filter, and then 10 images through the red, and then 10 through the green, and so on. Yes, yes, sir.
It seemed like you were using your eyeballs to note that jet, but are there certain frequencies that tend to yield more information or more revealing information?
Okay, so as you can imagine, we have all these different kinds of filters because each filter gives us a different piece of information. So usually we choose the filters for the science that we want to do. And for the most part, astronomers don't even make images out of their things. So what I noticed in that image, that little faint red line, is produced by hot hydrogen gas. But that gas is so hot that it should also be producing the red light produced by sulfur atoms. So when I first noticed that jet, what I then did is I scheduled observations to look at the same region using that sulfur 2 filter. And the telltale sign is if you see it in hydrogen alpha and sulfur 2 in the set narrow line, then it is one of those jets. So we use different filters depending on what type of object it is we're looking at and what things we want to learn. And that's why we have so many different filters. At Kitt Peak, there's over 100 different kinds of filters that we have available to us. Other questions? Yes, sir, in the back.
It seems like in the wintertime up here, when you go out and look up at the night sky in any direction, there's not very many stars visible. If you go down to the States, there's supposedly a lot of light pollution if you look up at the sky, and you're overwhelmed by the number of stars, both What's the explanation for that?
Well, it depends a lot on where you're going. So like, for example, when you say you went down to the lower 48, where were you when you were seeing lots of stars?
Oh, even in California, Colorado.
Oh, okay. So maybe at higher altitudes?
Well, not particularly. Some of it was at sea level. Of course, Colorado was higher.
Yeah, yeah. Well, I grew up in Colorado. When people ask me, how did I become an astronomer? It's like, I grew up in Colorado. I mean, the sky there is just spectacular. And that's because of the altitude. So when you get up to higher altitude, you're now above much of the water vapor in the Earth's atmosphere, which is why we put our telescopes up on mountaintops. So people often say to me, like, oh, I went on this cruise in the ocean, and we were far away from land, and the night sky was just spectacular because it was so dark. And that can be true. You can have some really nice night skies, but it's also true that when you get up to high altitude, it's not dark anymore. And that's because there's so much light coming from the stars that you can actually see the ground in front of you very easily. So I would guess for why you saw more stars in Colorado is almost certainly the altitude. With California, maybe it was in a drier location. It just really depends on the condition. I wouldn't say it necessarily has to do with the latitude. So being up in Fairbanks, being this far north, doesn't really affect how many stars you see, but being at a lower elevation might. Yes, sir?
You said that if you have a cloudy night when you're scheduled to use a telescope that you have to reschedule, of course.
Yes.
How competitive, or how many other people, what are you vying against? Is it pretty easy to reschedule? Or?
It's not easy at all, really. So basically the way it works is once or twice a year, there will be a time where a proposal deadline where you can submit a proposal asking for time on a telescope. So you write a multi-page proposal, describes what science you're going to do, what you expect to learn from it, what telescope you need, what camera and filters, how much time you need. And then what happens is that a panel of astronomers, actually it's many different panels depending on what topic it is, will review your proposal, and they'll rank all the proposals from best to worst. And for classical observing, what will then happen is someone will have the unenviable task of trying to schedule all the best proposals and fit in as many as it can. For Kitt Peak, it's usually on average about for every 5 proposals that are submitted, 1 will get time. But it depends on what telescope you want and how much time you want and other restrictions. For Hubble, the number can be higher. It can be as high as 8 to 1, 10 to 1. So it's actually very competitive. Now, in the case of what's called Q observing, Q as in like you're standing in a line, what happens is they rank the proposals from best to worst, and then they try doing the best proposal first. And if the weather's bad that night, then they wait till the next night. And then once that project's done, they move on to the next one, and they just get down as far on the list as they can. So if you're high on the list, you're almost guaranteed to get your observations. If you're low on the list, you're almost guaranteed you won't. And so that's the flexibility that allows it there. Now the downside is with the Q observing, you don't get to go to the telescope. And some of the most amazing experiences of my life has been standing on top of these mountaintops using those telescopes. So I do miss that. Yes, ma'am.
What do you think about these websites where people like us can rent a slot of time to observe ourselves, space, and do astrophotography?
So our question is, what about these different websites where you can rent time on telescopes? I think those are awesome. And if you haven't done that before, it's fun. It's a great experience. So anything and everything can be monetized and be put on the internet, and this is a great example of that. There's what are called robotic observatories, which are these remote observatories where it's completely controlled over the internet. And you can buy time on these telescopes, so you can buy like a number of hours or a number of nights, and then you can do whatever you want with it. And you can look at objects and make pictures, and I know lots of people who do that, and those are great experiences, so I definitely recommend it. I don't have one I recommend because all the telescopes I use don't work that way, and are much bigger. So, yes, sir, you have a question?
Do you find that as you become better known, do you have any better chance of actually getting any time on a telescope?
In principle, no. In principle, you're just ranked based upon the science, but like anything in life, if someone is highly productive and is a well-known scientist, and they know they have a strong publication record and are well-known in the field. Probably people, just being humans, tend to think of them. But I've been on many of these reviews, and I think we do in general, we do a good job to try to avoid that bias. And sometimes we get proposals from very big names that are garbage, and we reject them. So we know who they are, but they don't know who we are. So that allows us to be more impartial. Yes, ma'am.
So in making these images, there was some science you were pursuing, because obviously it takes more time if you have more images to take. It must have been a
Right.
thing. What?
So on these telescopes, about 98% of the time is for science. That is, the telescopes are scheduled strictly for the purpose of doing science, and occasionally some of the data we get from the telescope can be suitable for making an image. So as I said at the start of my talk, there's basically three reasons why we make images. The first and foremost is science. The second is we may have a new camera or a new capability that we want to show off to people, so we may get a little bit of extra time to do that. And then finally, we get a very small fraction of time, maybe a couple hours to a couple nights a year, where we just simply make pretty pictures. That is, we just look at objects because they're cool to look at. But that's a very, very small fraction of the time, and even that little amount of time we get for that is controversial among scientists. Scientists call these pretty pictures, and they like, why are we wasting our time with that? We should just strictly be doing science. So most of the images you see come from scientific observations, that is scientific observations done for the purpose of science. Sometimes, though, they are through these other methods as well.
So what is the science when you're doing such a heavy layer?
Well, so the science itself is not actually done with the color images. Sometimes we do create color images to help us visualize things because, like in the example of the Iris Nebula, making a color image allowed me to see something I wouldn't have otherwise noticed. Those little faint smudges would have been basically invisible to me until I noticed, hey, there's these little red faint smudges in a blue area. So that's an example where we do use visualization. We use these images for science visualization. But usually what we create when we look at an object with this camera, what we're more interested in doing is making precise measurements of like how bright the stars are, or the difference between the brightness and two filters, which again allows us to determine the temperature of the star, or do other things as well. So very rarely does an actual color image result in science. Now, unfortunately, because people only see the color images, they think that's how the science is done. That like if it was in a movie, we'd go to the telescope, click, take a picture, a beautiful image appears, we're like, oh, science, and we're done. But that's not how it works. In general, we don't create color images for the science itself. Yes, sir.
You just saw that you get information about the stars out of the image, but for example, when a star is moving, you always have the Doppler shift in it. Do you have a method to calculate it out, for example?
Okay, so he's asking about something called the Doppler shift. The Doppler shift, if you're not familiar with it, is the sound like if you hear a car coming towards you or a train coming towards you, the horn will have a higher pitch as it's moving towards you than if it's moving away. And the Doppler shift actually affects light as well. So if something is moving towards you, the light is shifted to higher energy, which is blue light, so it's called blue shifting. And if it's moving away from you, as you might guess, it's red shifted. It's the opposite. And in the case of stars, how much they move is actually very slow compared to the shift. It's such a small shift that you wouldn't notice it with these filters. But we do use a technique called spectroscopy, where we take the light from the object and we break it up into a rainbow, and there we can see the subtle shifts of the light moving there. It is true, though, for some galaxies that are extremely far away and moving very, very fast, that they will look redder in the pictures. And in fact, that's a good first step to see what are the most distant galaxies, the ones that look very, very red.
Thank you for the presentation.
Okay.
You're going to be out there?
Yeah, so I will be out there. So if you're interested in seeing a copy of the book or buying one or asking me more questions, I will be out there and be more than happy to talk with you more. So thank you all for coming, and I hope you enjoyed it.